So our guest today almost needs no introduction, but that's not correct. He was, for a long time, the Feynman Professor of Theoretical Physics at Caltech. He got his PhD at Princeton under the great John Wheeler, and he's been working on theoretical physics and particular moving more and more toward the discovery of gravitational waves for most of these decades. He's been elected to the American Academy of Arts and Sciences, the National Academy of Sciences, the Russian Academy of Sciences.
Self-finds wonderful.
The Russian Academy of Sciences. He says he had nothing to do with the election. He's been recognized by numerous awards, including the American Institute of Physics Science Writing Award in Physics and Astronomy, Phi Beta Kappa Science Writing Award, the American Physical Society's Littlefield Prize, the Robinson Prize in Cosmology from the University of Newcastle, Sigma Chi Scientific Research Society's Commonwealth Awards for Science and Invention, California Science Center's California Scientist of the Year in 2003, Albert Einstein Medal in 2009, the UNESCO Niels Bohr Medal, the Special Breakthrough Prize in Fundamental Physics in 2016, the Goober Prize in Cosmology, the Shaw Prize, the Kavli Prize, the Tumalia Prize, the Harvey Prize, and, oh yes, the Nobel Prize in Physics. By the way, since you're a big numbers guy, I did a back of the envelope calculation. There's been 923 people have been awarded the Nobel Prize. Since they've been giving it out, I estimate there's been about 12.5 billion people have lived. So you are one of 0.0000007785% of the human population. What's it like to win the Nobel Prize? To go there and get it? And
Well, let me describe what the first thing that happens is you're sound asleep. And at 2:15 a.m. there's this telephone call. So I went semi-naked into my wife's study where the telephone is and answered it. And the voice on the other end is the Secretary General of the Nobel Foundation, who said, "It will not surprise you that we're awarding you the Nobel Prize this year." And I responded, "It doesn't surprise me at all, but I'm very disappointed because it should have gone to the entire LIGO team that discovered gravitational waves, not to me." And I would have thought that by now,
right,
after the experience of the Higgs boson, which should have gone to the entire team that made that discovery and not to 3 individuals, you would have figured out how to do this.
Right, they have a rule. It can only go to 3, right?
That's right.
And no posthumous.
And so he said, "Well, we've been talking about that. We could change it, but we have not done so, and we'll be happy to continue the discussion with you when you get to Stockholm."
Yes.
which we did do. So,
do you think they would change that rule?
I don't think they will. But so the issue is that they see their role as promoting science worldwide, and they think that individuals are better icons for science than some organization. An individual is a hero, and so they're trying to make heroes and icons to promote science. On the other hand, and this is the argument I had with him, they also, I think, have an obligation to educate the world about the importance of collaborations, particularly in the modern era, and the power of collaborations, and the threat that certain major things such as this can only be done by collaborations. And so if they don't award the Nobel Prize to a collaboration, they really should invent something else, some other way to recognize collaborations.
Right.
That is a very high profile thing. So I think he buys it, but he said that even that is a very hard sell with the rest of the committee.
So they have a whole committee you would have. Now, once you win, do you have a little more say or power or influence?
Well, I get a lot more emails asking me to do things.
Oh, I see.
So that's the kind of influence.
Probably unpaid stuff, yes. Okay, so you go there and you give a lecture. Kip's lecture is online. You can watch it along with the other two.
Well, in our case, we also invited and paid for a large number of members of the collaboration to go. We couldn't get them into the ceremony. We couldn't get them into the banquet. We could get them into the lecture. So we had about 125 members of the collaboration there, went into the banquet, into the lecture. And then we set up 2 banquets for them separately. one that was in parallel at the same time as the prize ceremony and the official banquet, and the other one, I think it was the day before, where we were present, and it was the LIGO team, the key people at the National Science Foundation who had supported us, and key people at Caltech and MIT, which were the founding institutions.
How many people should be on the list of most deserving of that for the team?
Well, so the team, the way the Breakthrough Prize was done, 2/3 of the prize went to the team, and 1/3 went to individuals. And I thought that was a clever way to do it. So the team was really recognized in a major way, but they also had their icons as individuals. The way they chose to do it was they began with all the people who were co-authors on the discovery paper, which was 1,004 people.
Oh my gosh.
And then they went in and they consulted with various knowledgeable people, including the three winners, well, the two of the winners who, so in that case, Ron Drever was a winner, but he has dementia and wasn't really able to consult with him. But with Ray Weiss and me and a number of other leaders on the team, identified people who were not co-authors, but on whom the discovery built. And so there were an additional, I've forgotten, 12 or 15 individuals who had made major contributions but were not co-authors. The people who had spearheaded the numerical relativity, which was essential for understanding what LIGO saw by comparing with computer simulations. The people who had solved Einstein's equations analytically, approximately, to compute waveforms that were used in data analysis, so-called post-Newtonian approach. Those were the principal ones. And then Robbie Vogt, who declined to be an author on the paper, who was absolutely crucial as our first director. He's an interesting guy. He said, I will not be an author on the paper because I won't author a paper where I have not made a direct, immediate contribution.
Wow, okay.
And so they added Robbie on.
Oh, right.
And so things like that. And so it was done very carefully and I think with great wisdom by the Breakthrough Foundation.
Right,
And that's the kind
right.
of thing I think.
That's the, who puts up the money for, is that Google in part or Facebook?
No, that one is Yuri Milner.
Oh, that's right, yeah, Yuri Milner,
Yeah.
right.
Well, Yuri is the spearhead. I think the prize money comes from a combination of Yuri, the Facebook guy, Google guy.
Right.
But Yuri is the spearhead.
So for the Nobel, you actually get a medal. You have a medal?
For the Nobel?
Yeah.
Yeah.
Is it gold? Is it heavy?
It's gold.
Is it really cool?
It's solid gold.
Don't sell it.
It's solid gold. It comes with a ownership document which says this is owned by the Nobel Foundation. You cannot sell it.
Oh, really? No eBay.
But it is in your possession for as long as you should choose to keep it. And if you no longer want it, it goes back to the foundation.
So people put it in their trust or whatever.
They thought these things through very carefully.
Because didn't Einstein give his to his ex?
Well, he gave the prize money to his ex.
Oh, the prize money, but he kept the medal.
Yeah,
Okay.
yeah.
Today on eBay. Yeah. Okay. Well, that's pretty cool. So let's go back in time a little bit and kind of work our way up to how you came to work on gravitational waves. Two forms, history of science, but first your personal history. You were born and raised in Utah. You have 4 siblings, so 5 of you. Are you firstborn, lastborn, middle?
Firstborn.
Firstborn. See, firstborns are more likely to go into physics. There's research on this, Frank Sullivan's research. More traditional conservative professions. Anyway, so just saying, statistically speaking. So your mother was an economist and your father was a chemist. So there's obviously some academic encouragement there from an early age. And 2 of your siblings were professors. So what kind of nudged you toward physics?
So if I first got nudged toward astronomy, when my mother, when I was a kid, younger than 8, I wanted to be a snowplow driver. If you grow up in the mountains in Utah, that was inevitable. That was the most powerful job in the world. And then my mother took me to a lecture about the solar system, and I fell in love with astronomy through that. I was 8, and she encouraged me, helped me do some projects, and then I took off on my own reading about astronomy. And when I was 13, I ran into a book by George Gamow, who was a physicist and cosmologist of that era, called 1, 2, 3 Infinity.
Right.
In which the Tesseract appears. I know you want to talk about Tesseract later.
Yeah.
Anyway, so I fell in love with physics. What I came to understand from that book was that the laws of physics are really the foundation for how the universe works. And so I fell in love with that idea.
More than observational astronomy, say.
Yeah, well, the ultimate understanding of what the ultimate thing that underlies is the laws of physics. Observational astronomy tells you what's going on out there, but the laws of physics explain why it's going on, how it came to be,
right,
and how it can behave. And so, anyway, I fell in love with that at age 13, and so here I am.
So, okay, that's a little fast forward. So after Gamma. So, but back to the principle of the Nobel Prize. We like our heroes. Who did you look up to, or I'd like to be like this person, and do that kind of work for a living?
Well, I admired Gamow, and it's interesting that when I had just arrived at Caltech as a professor, I published a paper about the origin of magnetic fields in the universe and their growth. And I got a letter from Gamow asking questions about it. So I wrote back to him. I said that I was in this because of him, because of his book.
Nice.
And it had inspired me. And
what about Eddington? Did you read Eddington's?
No, I didn't read Eddington particularly,
okay.
No. But anyway, I told him that I had read it, I think, 6 times, and he sent me by return mail a copy in Hungarian, inscribed so that you may not be able to reread it a 7th time. So
that's funny.
He had a great sense of humor. So,
right.
So he was a significant influence on me. John Wheeler was a huge influence on me. He's my PhD thesis advisor at Princeton. Of course, Einstein was an inspiration, but.
As he is for so many people.
Yeah, that's right.
Yeah. So really, it's the, as you're a new professor, kind of nosing around for new areas to go into, is a lesson for any students out there, high school, college, undergraduates. What should I do? How do you sense where the action is going to be in decades from now? Is it like an intuition of here's some new areas that haven't been too exposed to research?
I don't know how you do it. I know how I made this decision. First of all, I understood myself well, and that I'm an introvert. I can play the extrovert and do play it very effectively, but I'm fundamentally an introvert, and I am much happier than working in an area that is not crowded, an area that might become very important in the future, but that is not yet recognized as such. And so I watched for things like that, and right from the beginning. And that's why I got into gravitational waves. Almost nobody was doing it, and
right.
I recognized what is now well known, that it could have a revolutionary impact on our understanding of the universe. And
what was the state of black hole research when you started?
There was great skepticism that black holes exist. Another person who had a huge influence on me was Jesse Greenstein. Jesse was an observational astronomer here at Caltech, a wonderful man, and I spent a summer working on my first academic research project with him on magnetic fields around stars and synchrotron radiation from electrons spiraling around in magnetic fields. Anyway, but he told me, when I told him that I wanted to go to Princeton, work with John Wheeler on relativity, his response was, well, relativity is not really very relevant to what goes on in the universe. Yeah, it's important for the Big Bang and the expansion of the universe, but I don't think it's going to be important for anything else.
Really?
And,
wow.
But that was the conventional wisdom among astronomers of that era.
Right. You mean that most of the things we observe can be explained with Newtonian mechanics?
Yeah,
you don't
right.
really need Einstein.
That's right.
But that's not true.
Well, that's not true today.
Yeah.
But it was true then.
Right.
And so the black holes were not recognized as things that might really exist out there by hardly anybody. Astronomers had no interest in them. The famous confrontation between Eddington and Chandrasekhar was related to that. Eddington's skepticism about the implosion of a star that might form something like a black hole. And that attitude was still pervasive in astronomy when I was a graduate student, when I was an undergraduate with Jesse here, and when I was a graduate student with Wheeler in Princeton.
Right.
And so again, that was clearly something that was worth getting into from my point of view, a lot of elbow room. And, but in my case, it was primarily my students. I sent them into that direction. They had a huge impact on the early research in what we call the golden era of black hole research.
In one of your lectures, you said 99.999% black holes are real, but you wouldn't say that about stars. You'd say it's 100%. There they are.
Yeah, well,
so,
the sun's there.
Yeah.
Well, now it's 100%.
100%, okay, yeah.
Thanks to LIGO, it's an absolute 100%.
Right, okay.
I mean, the shapes of the gravitational waves, the waveforms produced, that have been produced, well, that were seen by LIGO, match the theory beautifully. And this is not just for quiescent black holes. This is for two black holes that collide to produce a third bigger black hole, a very complicated process. And the theory is absolutely right on perfectly at the level of the observational data, which are quite good. And so
there's no other force in nature that could do that. Right, yeah. So when you talk about laws of nature, there's the things we see and then the underlying forces behind. What is a law? Where is it? I mean, it's almost like a Platonic ideal of the triangle that doesn't really exist, but something like that.
So the language of the laws of nature is mathematics. And so when we speak of the laws of nature, we talk about things like Newton's inverse square law. But even that very phrase is a mathematical phrase, that the gravitational acceleration that the sun exerts on a planet has a strength that varies inversely with the square of the distance from the sun. That's an example of a law of nature.
Right.
Or a physical law of physics. And so the laws of physics are couched in mathematical terms. There is also the question of how the various things that enter the laws of physics manifest themselves in the world, the observational interpretation of the laws. And so that's a little bit more, less 100% clear.
Right.
The mathematics is 100% clear. But where there have many times been sort of revolutions in our understanding of things like black holes and so forth, sometimes that's been related to not having properly understood the connection between the laws and the observations.
Right. But these aren't things that are just culturally constructed or they're linguistic tricks of the brain. I mean, there's something deeper because it's mathematics, not just language or words.
Well, it's deeper because it's mathematics. The issue is the connection to reality, connection to observation.
Right.
And I suppose you can be a solipsist and
well,
assume that nothing out there exists.
Right.
But still, the mental constructs that you build and the mathematical constructs you build as a solipsist, they certainly do a beautiful job of explaining the sensory impressions that come to you.
Right. Well, let's talk about gravity in that sense. I mean, we use this word. What is gravity? It's the tendency for objects to be attracted to one another. Why are objects attracted to one another? Gravity. But it's more than just a tautology of describing things.
Yeah. So even in the modern world, since Einstein, gravity is used much more broadly by physicists. Is more or less synonymous with the curvature of space-time. The gravity that we feel that holds us to the surface of the Earth is one manifestation of curvature of space-time or warping of space and time. But it's one manifestation that among a huge number of things. When you look at it mathematically, it's intertwined with other aspects of the warping of space-time very intimately. So one aspect of that intertwining that I like to talk about was something that Einstein realized already in 1912, whereas he didn't have his general theory of relativity until 1915. So this piece he understood. And that's what I like to call Einstein's law of time warps, that everything likes to live where it will age the most slowly, and gravity pulls it there.
Yeah, I have a hard time with that sentence.
But there's a mathematical formulation of that. Again, that's a law. There's a mathematical formulation. And from that mathematical formulation, you can look at the strength of gravity that we feel, and you can say how much slowing of time must there be on the surface of the Earth to produce that strength of gravity. And that prediction was made going all the way back to Einstein in 1912. And the measurements of this began around the 1950s with reasonable precision. Now the measurements are at a very high precision, a part in 10,000, maybe a part in 100,000, and it's right on. It's absolutely right on that time slows by precisely the amount that's required to explain the gravitational pull that pulls us here.
So I mean, I can picture the model that you always use on your slides that we see on television shows, like a rubber sheet with a huge bowling ball, and it kind of stretches it down. And so the planets aren't being pulled toward the sun by some mysterious force. They're kind of falling along this curved space-time, right? But that feels completely intuitively different than just that happens. This isn't falling around anything. It's just going straight down. I mean, but they are the same, or the manifestations of the same.
Well, the bowling ball analogy is not really very good.
Yeah.
It's heuristic. It gives you some sense that there must be some connection between the curvature of space and gravity. But in fact, the gravity that we feel is not caused by a curvature of space. It's caused by a slowing of time. And so that's a cheat in that sense.
Oh, man.
It's really the slowing of time that does it. And again, I use these words, but these are words that are designed to try to convey the idea, whereas the real law is the mathematical formulation of these words. And so these words are designed to give a heuristic sense of the mathematical law. But even I, as a physicist, as a professional physicist who's been doing this for half a century, I rely on these mental pictures. I rely on the picture of the funnel. I rely on the mental the words of the slowing of time produces the gravitational pull as intuitive aids to make guesses about what happens in the universe. Guesses that enable you, guesses in the form of intuitive leaps that are later verified or disproved by the mathematics. But as a working physicist, I need these aids in order to make rapid progress. You know,
Richard Dawkins made this point in one of his books about what he called middle land, that we evolved in the savannas of Africa with a brain tuned to middle-sized things, between, say, ants and mountains, but mostly just kind of middle-sized things, moving at, between a walking speed and a running speed. Lightning's pretty fast, maybe. But the idea of things like speed of light, expanding universes, quantum effect, these are completely counterintuitive. There's nothing to hang on in our brain to conceive of them. So we use these metaphors, to transfer this idea to that idea that we can hook, but you're losing things along the way.
Well, we develop these metaphors, and they begin to make sense gradually over time. And of course, they make more sense to me than they do to non-physicists. But they become part and parcel of how I think about the universe. It's very real to me. It's powerful to me, these metaphors. But for me, it's powerful because it's tied in a manner that I fully understand to the mathematics. But yeah, it's a little bit different from everyday experience.
But the metaphor at least gets you far enough to then do some math and see if the observations from the predictions based on that turn out. And if they do, then you know that it's not just a random metaphor. It's a moving toward a true metaphor, a small t. Well, so this brings up Interstellar. If you've seen the film Interstellar, Kip was the scientific consultant on that, worked on the script and so on. And it's an amazing attempt to depict the theoretical mathematical stuff that we can't really hook our brains around, us non-physicists, into something you can actually see on the screen. That must have been quite the challenge.
Well, that was very enjoyable. The visualizations that you see in there. So there are a variety of ways that science enters, but a very powerful one is through the visualizations of what things look like if you're near a black hole or near a wormhole or going through a wormhole. And those visualizations were produced by a large team at Double Negative Visual Effects in London. And they produced them by numerical solution of a variant of Einstein's equations. So I fed the equations to Oliver James, who is chief scientist there. He's a physicist, and he and I speak the same language. I fed him the equations for the propagation of light beams from some source of light, such as a very hot disk of gas around a black hole. The light beam travels around the black hole a few times and finally comes to the IMAX camera. And it's to the IMAX camera because Christopher Nolan insisted that this has to be realistic, as though it were done with an IMAX camera. And so all of the vagaries of the optics of the IMAX camera, the diffraction and light scattering, that's all in there. But that was Oliver's job. He hasn't had the model of the IMAX camera. I had the equations for the light propagation. But you wind up with images that are precisely what you would have seen through an IMAX camera in this situation. And so that was the joy of it. And everything you saw of that sort was from these simulations, with the exception of the trip through the wormhole, where we had to use a little artistic license because the actual trip was too boring.
Yes.
That was the only place that there was a
If you haven't seen the film, the plot, Matthew McConaughey plays this character, Cooper, who has to, the Earth is falling apart due to global warming and other environmental things, unlike in the 50s when it was nuclear weapons that were going to destroy the Earth anyway. These are always social commentaries on our own times, which is good. But he's got to go to this planet, the Miller planet, right? Circling a black hole. First of all, how would a planet have a stable orbit around a black hole? That's got to be tricky math.
Well, so when the movie came out, there were blogs and there were science pieces in newspapers and magazines about how this was all hogwash because the planet couldn't be that close to the black hole and be in a stable orbit. And they were all wrong.
Because you had already done the math on this.
Yeah, I'd already done the math. So I had written a book about the science of Interstellar, which explained all this. And the issue, however, was that Emma Thomas, who's Christopher Nolan's wife and the lead producer, and a force of nature in Hollywood, Emma was very concerned that if the existence of the book was known before the movie came out, that the movie would get labeled as a geek movie, and it would cut down on sales of tickets. So we were not allowed to let the world know this book existed until the day the movie was released.
Okay.
The book was released.
All right.
And so these science writers and so forth, they all got it wrong because they hadn't read my book because they didn't know the book existed.
Very
anyway,
good.
some of them ate crow publicly after they saw my book.
You tell this funny story about how Christopher Nolan, the director, wanted the Cooper character to age at a certain rate. So he ages an hour and his daughter ages 7 years. Because later in the movie he comes back and his daughter's older than him now. Well, all right, so and the funny part of the story was that you said, no, that can't be. And he goes,
No.
Yes, it can be. Go back and make it work. So he just had an intuition that somehow their math would work.
Well, I think his intuition had a little different basis. I had worked for several years with his brother on the first 3 drafts of the screenplay, and we had developed a very good working relationship. And then I had the similar kind of working relationship with Chris, as Chris did the last 3 drafts of the screenplay. And there were a number of occasions when his brother Jonah or Chris would say, I'd like to do something, this, that, or another thing in the movie. And I would say, well, I'm a little skeptical that's going to work. And they would say, go think about it. And so I go home and think about it, do some calculations, sleep on it for a night or two, and found some way that it worked. And so he had that experience, and as had his brother. And
so the time warping comes either through traveling very close to the speed of light or being very close to a black hole or a high gravity.
Well, in this case, the time warping comes from being very close to a black hole. The issue is how close can you be to a black hole and be in a stable orbit. If the black hole doesn't spin, you can't be very close at all. And that was the issue. And all of my intuition and the intuition of the bloggers and science writers was based on non-spinning black holes. When I went in and did the calculation for a fast-spinning black hole, I found that if you make it spin fast enough, you can get just as close to the horizon as you want and still be in a stable orbit. Basically, in some sense, the centrifugal force associated with the dragging of space into whirling motion, like the air in a tornado, stabilizes the orbit, and even down very close to the horizon. And so it turned out that we could get what Chris wanted. 7 days, 7 years on Earth is an hour on Miller's planet.
So this is true. You could go out, say, near the speed of light or near a black hole, come back, and your children are older than you.
Yeah.
That's real.
That's real.
And we know that from clocks that are flown in space. Or there was a story the other day about another super atomic, a better atomic clock or something, brought close to a mountain range or top of a mountain versus the bottom of a mountain, and it was just the right.
Well, that's precisely Einstein's law of time warps. Again, that's the slowing of time on the surface of the Earth.
But why does it do that?
Because that's what's required to produce the gravity we feel.
Okay.
So
sure.
So why does it do it? Because the mass of the Earth slows time.
Okay, but just try to say it another way.
The mass of the Earth slows time. That slowing of time produces the gravitational pull we feel.
So if it's a cesium atom or whatever bouncing in a little measuring device, and the number of vibrations slows a tiny bit because of the gravitational pull, so that clock slows a little bit. I kind of get that. What would be the equivalent of that in my body that's slowing slower than your body because you're on Earth?
Everything.
Everything. I mean, just atomic motion in cells.
All atomic motions in cells, your heart, everything. Your body and the cesium clock are all regulated by the flow of time, which is part of the structure of the universe. Of course, there are other things that can influence it, like taking speed or something. But all physical processes and biological processes are regulated by the flow of time, and that flow of time slows near a massive object.
And just to be clear, on the Miller planet and Matthew McConaughey's watch and his box where he's in his spaceship, all that, he doesn't even know that things are slowing down. His clock is just ticking as normal. Yeah, it's only relative to some other frame of reference, right?
Yeah, that's right. You're only by comparing with what's going on somewhere else in the universe do you discover that this slowing is going on. There's absolutely no manifestation of it in your neighborhood. Everything's completely normal in your neighborhood.
Right. So I kind of get that, moving forward in time, I'll just say it that way, there's different frames of reference, so different speeds of moving forward in time. But how could you go back in time?
Well, the only way you can go back in time, if it's possible, is something that respects the fact that locally you always are going forward in time. So somehow you have to go always forward in time, but make a trip out in space and come back before you started. So it has to be related to the structure of space and time on large scales. And so any kind of a time machine for going back in time, if such things are allowed by the laws of nature, you go forward in time, but you go make a big trip around and you come back before you started.
Through a wormhole or something like that?
Through a wormhole. It doesn't have to be through a wormhole. If you have, for example, in general relativity, if you had a very, very rapidly spinning cylinder, this is the solution of Einstein's equations found by a guy named Van Stockholm in 1937, if my memory's right, before I was born. A rapidly rotating cylinder made out of exotic matter, strange kind of matter, then you could go around the cylinder and come back before you started.
Now, early in the movie, McConaughey's daughter, Murph, has some weird, spooky, like paranormal ESP kind of stuff, like a book comes off the shelf and her hands, I think the hands on the watch are acting goofy. And then later we find out it's him, her father, making these things happen. How could he go back to her childhood?
So he doesn't. What happens is that he's gone out in the universe and come back, but he doesn't come back before he started. He doesn't come back to her childhood. So let me just back up.
Yeah,
okay?
yeah.
Let me back up.
Walk us through this.
So one of the first things I learned from the Nolan brothers is that they have, when they make a science fiction movie, they have their analog of the laws of physics. And they call it a rule set, a rigid rule set. And this is our rule set for how space and time operate. And their rule set is identically the same concept as my laws of physics in a domain where we don't know for sure what the physical laws are. And so we can speculate. And the rule set that they imposed on this film in consultation with me was that no human being can go backward in time. Nothing can go backward in time in our universe. But there is also the fifth dimension, which is outside our universe. And things can go backward in time in the fifth dimension, but humans cannot access the fifth dimension. The only thing that can access the fifth dimension, and this is real physics now, this is Einstein's general relativity carried into the fifth dimension. The only thing that can access the fifth dimension is gravity. And so in the fifth dimension, by their rule set, there are what I, as a physicist, called closed time-like curves. In the fifth dimension, things can go backward in time, but the only thing that we can access the fifth dimension by is by gravity. And so there is the Tesseract that Murph is in one face of the Tesseract. The Tesseract is a cube with 4 dimensions, has 3-dimensional faces. And we are 3-dimensional beings. We can live in the faces of the Tesseract. We can't access the interior because that's part of the bulk. It's a 4th space dimension or a 5th space-time dimension. That's what is the 5th dimension in the movie. And so what Murph is in one face of the Tesseract. Her father, Cooper, is in the other face of the Tesseract. He pushes on a structure to produce a gravitational force that goes through the interior of the Tesseract, which is in this higher dimension. And that gravitational force goes backward in time and influences her watch. But you wouldn't know that based on watching the movie.
Oh, okay.
However, if you watch the movie 7 times, you might notice.
On the 7th time?
On the 7th time, you might notice that Amelia Brand, when she and Cooper, that is when Anne Hathaway and Matthew McConaughey are sitting in the Ranger on Miller's planet in between giant tides, giant waves washing over their spacecraft. And they're having sort of philosophical discussion waiting for the next wave. She makes remarks about maybe you can go backward and forward in the higher dimension.
Okay.
And this is a thing that if you're an aficionado of Christopher Nolan, you may not realize that his movies always have puzzling aspects, but somewhere in the dialogue, never in the place where the puzzling thing happens, but somewhere else in the movie, in the dialogue, is the key to understanding what happens.
A little Easter egg he plans for you to find later, yes, okay.
So you go in out in the 7th viewing, you may notice this dialogue, and she basically tells you that this is what's going to
Okay.
happen.
I'm trying to remember, to get to the Tesseract, he goes through the black hole, right?
Yeah, so he goes into the black hole. He approaches the singularity, which is what is called a gentle singularity by, what's his name, Anomaly, who's the theoretical physicist who's killed by Kip, the robot. And so Anomaly, it talks about this gentle singularity. And he falls into the gentle singularity, which doesn't kill him, and he's scooped up by the Tesseract, which is a space vehicle that goes into the higher dimension and carries him up into the higher dimension and back to Earth. And while he is, you see him kicking and screaming, him being Cooper or Matthew McConaughey, kicking and screaming in the Tesseract. That's while he's being transported back to Earth. So by way of further explanation, let me just say that the first, maybe the second meeting I had with Chris about details of the movie, he said to me, I have always admired Stanley Kubrick's 2001: A Space Odyssey, especially the ending, which is almost impossible to understand. And I want to do the same thing in Interstellar.
Leave everybody hanging.
But
What did it mean?
But I want it to be explainable. And so his, later on he said, you can explain it in detail in your book. And so I got the pleasure of being the explainer. And so what I'm saying is in the book in some detail. But the explanation is, as I say, also in the film to some degree in dialogue of Amelia Brand earlier in the movie.
I actually write about that a little bit, not that I understand it. In my latest book, I have a chapter on anomalous psychological experiences, just weird things that happen to people. What's the explanation? And I don't believe in the supernatural or the paranormal, so if it turns out these things are real at some level, it would have to have an explanation like this. It still has to be within the laws of physics. And so I admire that you were able to deal with the Hollywood and still get your principles across without having to sacrifice for the plot.
Yeah, well, it was a joyous collaboration for
and that has to be
Chris
super
and me.
unusual for science fiction. Science fiction writers usually complain about.
Yeah, well, the key to this was that the science was built into the film from the outset. The movie sprang from a treatment that I co-authored with Linda Obst, who's a former girlfriend of mine in Hollywood. A producer. She did things like Fisher King, Sleepless in Seattle, Contact, How to Lose a Guy in 10 Days, The Art of Lying. She's very versatile. Anyway, she and I wrote the treatment from which the movie sprang, and we built the science deeply into the treatment. The treatment was about 1/3 science and 2/3 basically a story of a way the science was integrated into a story. And the Nolan brothers came on enthusiastic to preserve that science and to make a movie that respected the science. And so the nature of the collaboration was a true brainstorming collaboration between me and them over the science in the film throughout the process of writing and perfecting the screenplay.
I was stunned to hear you say it was 10 years from inception and starting the screenplay to the actual film being screened. That's stunning. That's a huge amount of work.
That's not, well, most of the time it was sitting on a shelf.
Oh, yeah, right. So you have another one in the works.
Yeah, I have another one that, in this one, it springs from a treatment that I co-authored with Stephen Hawking and Linda Obst. So Linda and I brought Stephen on as a collaborator on the treatment. And so we are now about where Interstellar was around 2010. That is, we are into the second draft of the screenplay. The screenwriter, I mean, we have a studio, a director, a screenwriter, and the screenwriter has just finished the second draft of the screenplay. And I've been spending the last several days going over the science in the second draft and writing voluminous notes about it, doing lots of calculations. So we're doing the same thing with
So that might be out in 3, 4, 5 years.
Yeah, I would say if we're lucky, 3 years. If we're unlucky, infinity.
So what's it like to go to, I asked you what it's like to go to the Nobel Prize. What's it like to go to a Hollywood screening and the stars and all that stuff? That must be fun.
So, well, what I've been to mostly are Academy Award parties. which occur at this time of year when they're trying to promote their movies to members of the Academy. And I was told by Linda Opes when I started going to these with her that you dress like this. You wear jeans, you wear an open-necked shirt or a turtleneck, you wear a nice jacket, and that is Hollywood
This
formal.
is the Hollywood look, okay.
So I thought I would come in Hollywood formal dress. It's not the formal dress of an Academy Award, but it's the formal dress for things like Academy Award parties.
Right.
That precede the voting on the.
Right.
You know.
So it won an Academy Award for special effects, right?
Yeah, it won 7 Academy Awards, but not the major ones of director.
Right. Right.
Chris is up for the major ones for his next film, which is Dunkirk.
Oh, right.
So in the announcements, I guess March 3rd, and so this time he's up for Best Director and Best Picture.
Does it involve gravitational waves by any chance?
Dunkirk doesn't.
No, not Dunkirk. Yeah. No, your next film.
I'm not allowed to say.
Oh, okay. All right. Okay.
So when we write a treatment, we sell to a studio an option to make a movie based on the treatment. The studio has a certain period of time, I think 3 years in this case, to exercise the option and actually buy it, and so that they're committed. And so the contract that I sign, selling them the option, says I will not reveal to the public anything about the movie that is not already in the public domain. That is, the studio reserves the right to leak information in whatever manner and wherever they wish.
Very interesting.
And strategic leaks are designed to maximize ticket sales, obviously.
Yeah. Let's go back to Newton and talk about gravity, and then fast forward to your current work. So would you say that Newton got it wrong, or that Einstein complemented it or tweaked it, or how revolutionary was Einstein from Newton?
So Newton had a mathematical description of gravity, a description in terms of physical laws that is highly accurate under normal circumstances. Einstein, motivated by other things unrelated to gravity, had a tremendous insight in 1905. And the way I like to say it is that Einstein identified a physical law that governs physical laws. And all of the physical laws have to be compatible with his overall governing law. His overall governing law is called the principle of relativity, and this governing law was violated by Newton's laws of gravity. And so already in 1905, he said to himself, I know Newton is wrong because his laws of gravity violate my law that governs laws.
Wow. I think you called that chutzpah.
Real chutzpah. These are not the words that he used, but I think this is an accurate description of what he did. And so he began the search for something that would be more accurate and that would reproduce what Newton said to high accuracy under normal circumstances, but that would be in accord with the fundamental principle of relativity.
Were there, in a sort of Kuhnian way, accumulation of anomalies that were not explained by Newtonian mechanics that needed a larger?
There was not much, and that's the strange thing about this. There was the perihelion shift of Mercury, and that was it.
Wow.
And there were other ways to try to explain the perihelion shift of Mercury. A slight modification of Newton's laws of physics that Newton didn't get quite right. This was one speculation. The planet Vulcan, which they never found, but which would have, if it had been there, could have produced that perihelion shift. So there was one anomaly, only one.
Wow.
And the genius of Einstein was that he recognized, without even looking at that anomaly, he recognized that something had to be wrong with Einstein's laws of gravity, and he went after it. And in the end, he developed a theory, a set of physical laws, his general relativity laws, that did explain the anomaly. But the anomaly was not a driving force in what he was doing,
Right.
which is quite different from other Kuhnian revolutions.
So this is the role of thought experiments and just thinking deeply on a
Thinking
problem.
very deeply on a problem.
Yeah.
Yeah.
Good to work at a patent office when you have a lot of free time sitting there, maybe.
That's right. Well, good to have the mind that Einstein had.
Well, yes. I guess you would put him probably up in the top half dozen most important.
Well, no, I would put him at the very top.
Of scientists, yeah.
Well, at least a physicist,
Yeah.
even above Newton.
Yeah.
That doesn't mean he was perfect. He had tremendous physical intuition, an intuition about how nature works. He was a mediocre mathematician. By mediocre, I mean he was sort of like me. He sort of muddled along at the level that enabled him to do what he needed to do.
So what is it about, I think it was in 2015 is when the gravitational waves originates, right, in theory?
So in theory, it was 1916 when he predicts gravitational waves.
Oh, okay.
It was 2016 when we announced the discovery.
So perfect century.
So it was a perfect
Nice.
century from the prediction to the announcement of the discovery. But the team, our LIGO team, made the discovery in 2015.
Maybe explain to us what, when we think of space-time or just space or whatever, here there's space, and we think of, again, the analogies or metaphors, ripples on water. There's water that's rippling. What's rippling? What's a gravitational wave rippling through?
The shape of space.
The shape of space, yeah. Okay, what does that mean?
So one way to describe what a gravitational wave does is that as it goes through you, from me to you, it stretches space in this direction and squeezes space in that direction.
Okay.
And then a moment later it stretches in this direction, squeezes in that direction. And you ride on space. And through this, it stretches and squeezes you. So, but the thing that really is the marker on space is inertial reference frames, or inertial particles. And so if you lay down a bunch of particles in space, and they're just sitting there moving, or not moving inertially, just influenced only by their own inertia, when space stretches, they move apart. When it squeezes, they move together. They're markers for what space is doing. If they're particles, they don't interact with each other. There are no forces acting on them whatsoever. They're just riding on space.
Okay. So this is the interferometer where you have these L-shaped.
That's right. So an interferometer is designed to measure this effect.
And I was just stunned to read this, or one of your lectures say it was, the movement is 1/10,000th the nucleus of an atom.
Yeah.
I mean, how could you even measure that? What kind of possible technology can do that? It's just,
Well, so that's the level of the noise in the instruments that made the measurement. The actual motion was 1/100th the nucleus of an atom.
Oh, okay.
But the noise was about 100 times smaller.
Oh, okay.
So we're capable of seeing things at that level.
Wow.
And are moving toward a factor 10 better than that in a few years. So how is that possible? That's what I asked myself. Ray Weiss, my close friend and collaborator at MIT, who was the primary inventor of the technique that was used, he described a detector like LIGO uses, his invention paper. And he said you hang mirrors from overhead supports, you let the gravitational wave act and it moves them back and forth, and you use laser beams that bounce back and forth between the mirrors to monitor that motion through a technique called interferometry. But the key thing is you're using a light beam between mirrors to monitor the motion. and I knew how, with pretty good confidence, how strong the waves were by that time. I was a theorist. I'd been working on sources of gravitational waves for a few years. And he knew what I and my colleagues were predicting. And so we knew more or less where we were going, and we had it right on. The strength of the waves that we were predicting at that time is the strength of the waves that LIGO saw in the end. But the level was, a better way to say it is a trillionth the wavelength of light that you're using to make the measurement.
Wow.
And when I saw that number, that you're going to use light to measure the motion of mirrors at a level that is at 1 trillionth, 10 to the minus 12 in scientific notation, with the wavelength of light, I thought this is ridiculous. And so I was in the, when I first heard this, I was in the process of, with John Wheeler and Charles Misner, of finalizing the text of a textbook on relativity called Gravitation. This was 1972. The book went to press in September of 1972. I first heard this sometime in the summer of 1972. I didn't have the benefit of discussing it with Ray Weiss. I had not read in any depth the paper he'd written on this, because he published it in an internal MIT report, not in the regular literature, because he said that you shouldn't publish something like this in the regular literature until you've built the instrument and seen the gravitational waves. So,
wow.
And so that was his attitude. So I very quickly just put in a sentence in our chapter about detection of gravitational waves, describing this technique and saying this is not promising. And Ray has never let me forget that.
That's funny.
In the end, I ended up spending 60% of my career helping him and his experimental colleagues.
As a technical question, how do they control for, a truck drives by, somebody sneezes? I mean, just all these little, the earth moves and...
You have, so if you go over a bumpy road in a suitable car, a Cadillac, not my wife's BMW Z4 that has a very tight suspension, but in something with a very soft suspension,
okay,
you don't notice the bumps.
All right.
And so you want a very, very good suspension, like in a Cadillac. And so that, in fact, is what is used. Such a suspension is based on masses and springs in a Cadillac, and that's one of the techniques that's used here. So you basically have to have an enormously effective mechanical isolation of your mirrors from the external world. They have to be isolated mechanically, thermally, in all respects, so that nothing makes them move except the stretching and squeezing of space. That's why this thing cost $1 billion and required 1,000 collaborators.
Right, the engineering is incredible. Are they located in any particular place for that reason, or is it just what was available?
They needed to be as far apart as possible because you wanted to know whether you're seeing the same thing at different locations, and you don't want to have common noise from, for example, seismic motions or magnetic field fluctuations. And so you wanted them far apart. You also want them far apart because the way in which you determine the direction to a source is from the time delay in the arrival of some feature in the signal at several different locations. So if the first signal that came in arrived in Livingston, Louisiana, 7 milliseconds before it arrived in Hanford, Washington. And so we knew that the source was somewhere in the south.
And didn't it happen just like moments after you turned it on? Or an hour or something like that?
Yeah,
I mean,
well, the first, so when we, this project was a long time in gestating. Ray and I both started working on foundations for it in the 1960s, so for us it was 50 years. We built a collaboration between Caltech and MIT, he and I and Ron Drever, who was the experimenter at Caltech, in the early 80s, and we submitted our proposal in 1989 to the National Science Foundation to build this thing. In that proposal, we said we would have to go through, we would very likely have to go through 2 generations of instruments. a first generation that would have to be very lucky if it saw anything. But that was essential in perfecting the technology and the techniques. And then the second generation would be at a sensitivity where we would be likely to see things. So Barry Barish came on board as the director who really made this thing happen, built the LIGO team, and led us through this process. And so the team began installing the first generation in about 2000. And it operated between 2000 and 2010. And the second generation began installation in 2010, and it began operation in 2015. Not at design sensitivity, a factor roughly 3 times worse than design sensitivity, but a factor of about 3 improvement on the first generation. Those 2 instruments, one in Hanford, Washington, the other in Livingston, Louisiana, were in the process of being tuned. They're very complicated and complex instruments. They had to be brought into the state you wanted for the beginning of the search. And the search was planned to begin, I think, 3 days in the future when the first signal came in. So they were almost ready to begin the search. And the first signal came in, and the director of LIGO, who was David Wrightsey, now Barish had moved on to lead another project that had come back now, but David Wrightsey was the director. David declared the search has begun because this first signal had come in.
Yeah, incredible.
But so the signal came in about 3 days before the search was intended to begin. So they froze the instruments in the state they were in.
Right.
They were almost in the state that was planned, and moved forward with the first observational run, which lasted from mid-September to something like mid-January. So about 4 months.
So the first observations confirmed your theoretical predictions of 2 black holes circling and then colliding. If new information came in, how would you know how to interpret it? Like, this has been described as a new form of astronomy. We had light, radio telescopes, and now we have these. What might we find?
So we were targeting from the outset colliding black holes and colliding neutron stars, and black holes tearing neutron stars apart. Binary systems of black holes going around each other, or neutron stars going around each other, or a black hole and a neutron star. We have now seen the black hole binaries. We've seen the neutron star binaries. The next thing I expect to see is a neutron star black hole binary. The black hole tears the star apart. We also expect to see gravitational waves from spinning neutron stars that have, roughly speaking, mountains on their surfaces, deformed neutron stars. Because a neutron star is a solid object, and it can be deformed just as any other solid object can be. So we expect to see that. If we're lucky, we'll see gravitational waves from exotic phenomena in the early universe, such as cosmic strings. But the most interesting things will be the huge surprises. And every time that humans have opened up a new way of observing the universe, there have been huge surprises. And gravitational waves, the difference between gravitational waves and electromagnetic waves, the other way, is far greater than the difference between any other 2 ways of observing the universe. So the surprises we expect there will be surprises that are huge, huge, huge surprises. But there is a problem of if you see a surprise signal, how do you interpret it?
How do you know? Yeah.
And so that will be a struggle. That
right.
will be a struggle.
It's the unknowns. Yeah. So there you're going from observation to, well, half a dozen hypotheses of what it could be, and then you gather some more data. What about the possible explanation for the origins of the Big Bang, or all the way back to the beginning, whatever that means?
So the origin of the Big Bang is almost certainly governed by the laws of quantum gravity. And those laws of quantum gravity, the best candidate set of laws, as yet still in a incomplete form, are the laws of string theory, or M theory. And ultimately, I think some variant of this, or some others, whatever the correct laws of quantum gravity are, will be the thing that will govern the birth of the universe. And we will understand the birth of the universe probably through combined astronomical observations with gravitational wave detectors primarily, and development of the theory of quantum gravity.
If there's multiple universes,
But we're not there yet.
Okay, we're not there yet.
And so you can ask, what came before the Big Bang? What was the nature of the Big Bang?
Yeah.
My answer is I don't know. My answer is that that's the most important problem in theoretical physics today. And my
Really?
Answer, and my answer is that I have refused to work on it ever in my career because as I said earlier, by personality, I don't want to work in a crowded field. And if there's an overcrowded field in physics, it's that. So it's not for me. That's why I did gravity waves instead of quantum
Right.
gravity.
Well, of course, we get the typical American theist answer is, well, God did it. Yeah, I mean, you must get this all the time. You must get letters.
I find that a very boring answer.
Yeah. Well, it doesn't explain anything.
Yeah, precisely for just that reason.
Right.
For me, to me, it's a boring answer because it is not an explanation that, at least at this stage, we have any way to test. Whereas the tools of science that we work with are fully testable, and their triumph is their ability to explain what we see, and their ability to make new predictions that are verified, their ability to be a foundation for technology that makes the world better.
I mean, either we want to know, well, where did God come from, who created God, or how did God do it? Did God use quantum gravitational forces or whatever? I mean, it's a little bit like the God of the gaps argument. We just keep pushing the gaps, filling the gaps and pushing the initial cause further back. If there is a multiverse, and I'm way out of my league here, but I remember something about brains, colliding brains, BRANES, as a possible theory about this could trigger a universal Big Bang or something like that. Could a colliding brain create a gravitational wave that we could detect, and you could test the multiverse or something like that? Or is that just crazy?
I think the answer is yes, but then there would be the issue of interpreting what you saw. And we will very likely see some sort of stochastic background of gravitational waves that comes from something very interesting in the early universe. It might be colliding brains. That's not likely, but conceivably it could be a phase transition in which the laws of nature changed. There is a firm prediction that the electromagnetic force didn't exist at the beginning of the universe. But it came into being in a phase transition, a sudden change in the nature of the laws of physics, when the universe was about a trillionth of a second old. And there's a prediction that this may have occurred. It's not a firm prediction. Is a first-order phase transition inside bubbles that are rather like droplets, like water droplets that condense out of water vapor. But these bubbles are predicted to expand at the speed of light, collide, produce a strong burst of gravitational waves in those collisions. And the theory says that those waves should have been shifted to longer wavelengths as the universe expanded, and that today they have wavelengths that are comparable to the distances between the planets.
Wow.
And could be seen by an analog of LIGO in space, where the arm lengths are millions of kilometers instead of 4 kilometers.
Now that's an engineering project.
And that's an engineering project. It's called LISA, Laser Interferometer Space Antenna. It began as a NASA mission. It is now a European Space Agency mission. In the George W. Bush administration, the U.S. pulled out of that because of cost overruns on the James Webb Space Telescope. And so now the Europeans are doing it. The Americans want back in.
Right.
That mission is tremendously exciting. It will very likely launch around 2030.
All
And
right.
we could be seeing gravitational waves from the birth of the electromagnetic force. But being sure that's what that's from, that's going to be a big struggle. But that is a concrete prediction that is a pretty high probability prediction of waves from the earliest moments of the universe. There will be others, I'm pretty sure, that over the coming decades, a large part of the effort in gravitational wave astronomy and cosmology is going to be exploring the first 1 second of the life of the universe with gravitational waves, seeing things, struggling to understand them, going back and forth.
This could go on another century or two of development.
Yeah, well, the way I like to describe it is that there are only two kinds of waves that can propagate across the universe, bringing us information about what's far away: electromagnetic waves and gravitational waves, and that's it. Astronomy until now has been based on electromagnetic waves: light, radio waves, X-rays, gamma rays, infrared, ultraviolet, and so forth. Galileo started electromagnetic astronomy with telescopes 400 years ago. LIGO opened up gravitational astronomy for the first time 2 years ago. And so now we have the other kind of wave in our hands for observations. When you look at what we've learned about the universe with electromagnetic waves since Galileo's time, you can then speculate about what things will look like 400 years from now,
Right.
from gravitational wave observations. And it's that expectation that is the reason that I was not at all surprised when the Nobel Committee
Right.
gave the prize to LIGO for discovering gravitational
Is this
waves.
an exciting area for youngsters to get into? People interested in
It's a
physics?
tremendously
Yeah.
exciting area. It's not an area that I would go into because it's too crowded. But for those who enjoy working in a big collaboration, it's tremendously exciting.
Yeah.
The things that are being discovered, the things that have been discovered by LIGO and now Virgo, a similar instrument that has now begun to operate in Europe. The things that have been discovered already are really fantastic.
So are you starting to move away from actively working on that and working more in bringing science to the general public through films and things like that?
Well, I got out of LIGO as quickly as I could because it was too crowded. So I trained a new generation of younger physicists who could play the role that I was playing. And so I, in collaboration with some of these younger people, I wrote the science case for the advanced LIGO detectors in 2001. And then I abandoned day-to-day involvement in LIGO, but I then spearheaded the creation of an effort in computer simulations of colliding black holes that was crucial for LIGO. Starting that at Caltech, Lee Lindblom, who was on the research faculty, and I initiated that in about 2001 when I pulled out of LIGO. And so I pushed that hard, not writing code, not doing the numerical relativity, but providing the vision for where that went. And I'm still somewhat involved in that. But I also then, in the late 2000s, began a gradual transition to a new career. I figured I had been a conventional professor for nearly 50 years, and for my next 50 years, I wanted to do something else. And so,
Well, the visual medium is the biggest classroom in the world.
Yeah, so I'm just enjoying now the new career that the transition is nearly complete, which is collaborations with filmmakers, artists, and musicians.
Are you at all worried about the future of science in either the Western world or America in particular? You've gone through many political administrations in your career. They're more supportive, less supportive, and so on. Is this a different time now? Are you concerned? Or
I'm not concerned about science on long time scales. there are short-term bumps, as with this particular administration in Washington. But the Republicans in Congress have been very supportive of science, just as the Democrats have been. So I'm not particularly concerned about that. I am very concerned about the world under Trump, who frightens the bejesus out of me.
Yeah.
What he could do in terms of a nuclear war, just because he got up on the wrong side of the bed this morning. It's just tremendously frightening. But I don't worry about science. I worry about other things.
Okay.
Like that.
Yes. Well, those are legitimate concerns. I have high hopes that Kim Jong-un just wants a chair at the table and is just doing it for deterrence. But that's another subject, I guess. Well, thank you for what you do. Thank you for your supporting the skeptics and the public understanding of science. And of course, thanks for changing the world with your research.
Well, thank you. And
Let's thank our guests. Thank you.
Thank you.
We have a pretty smart audience. I have a feeling we have some good questions coming. Who would like to start us off? Yes, sir.
Are gravitational waves subject to the type of phase coherency relationships of, say, sound waves, of phase cancellation and things?
Yeah, so gravitational waves, like all other forms of waves, can superpose, they can cancel each other, they can reinforce each other. All wave phenomena share that. But gravitational waves share even more than that, say with electromagnetic waves. Like electromagnetic waves, they propagate at the speed of light. They can be gravitationally lensed. They experience redshifts in the same way as electromagnetic waves. The reason is that if you have gravitational waves or electromagnetic waves, when the wavelength is very short compared to other things that are around, they behave more or less the same way in the so-called geometric optics limit. So if the wavelength is short compared to, for example, the radius of the sun, then they will bend, the gravitational waves will propagate along the same kind of light rays, same kind of rays as electromagnetic waves, and they'll bend around the sun due to gravity. But on the other hand, the gravitational waves are tremendously penetrating, so they'll travel right through the sun and still bend due to the mass that's in the core of the sun. So they're different in the sense that they're tremendously penetrating, but in vacuum they behave the same way as electromagnetic waves.
So, this is going to sound dumb because it's like I didn't listen or something, but so we know, because a baby opens his eyes, that there are electromagnetic in his ears, there are electromagnetic waves, and now we know there are gravitational waves, but you know that there are only electromagnetic waves and gravitational waves that can propagate through the universe. How sure are you that you're not going to find a third one?
Something else, yeah. Yeah, that's right, an unknown.
It's conceivable that there is another type of wave that can propagate through the universe. So waves, fundamental types of waves like this are associated with particles and are carried by particles. So electromagnetic waves are carried by photons. The photons behave like a wave when you have huge numbers of them all doing the same thing. Then they act like a wave. If you only have a very small number of them not doing the same thing, they act like particles. That's a weird thing about physics. But what you need, and the kinds of particles that can then behave like a wave, they also have to have integer spin, which is a crazy concept in physics. But photons have spin 1, gravitational waves have spin 2, and why nature doesn't, and zero rest mass, and that's what makes a wave that propagates at the speed of light. Why nature has not given us a zero rest mass spin 0 particle that makes waves, I don't know. Nobody knows.
What's the particle?
So it would make a scalar wave, and there is no such particle that has ever been found, but it would make a scalar wave which would be a third kind of wave that could bring information from far away. But we have no evidence that such a thing exists. It's not part of the current laws of nature, but it could. Conceivably, it could exist. So we're not 100% sure. We have no evidence at all for the existence of that kind of particle. There is the Higgs particle that gives mass to other particles is a scalar particle, but it itself has mass, and it can't form a wave that propagates at high speeds through the universe because of that. So we don't know of any other, but nothing in the laws of nature that we have says there could not exist this third type of wave. It's just that we have no evidence whatsoever for either the particle associated with it or the wave or any manifestation of it whatsoever.
All you need is $1 billion and an instrument.
Sorry to get a little technical, but
there we go.
So if we follow up on that just a bit, you talked about our ways of seeing across the universe and only two versions of waves. But if I look at, say, neutrinos,
that's right,
which don't make a wave, but they do travel either at the speed of light or very close, depending on their mass, isn't that another?
That's another way. So there are neutrinos and there are cosmic ray particles, and they have also brought very important information. They bring much less information than the gravitational waves or the electromagnetic waves, but they bring very, very valuable information. So for pedagogical purposes, I focused on waves, not wanting to, but you're absolutely right. Neutrino astronomy will play hand in hand with gravitational astronomy and electromagnetic astronomy, will play a huge role in the future, particularly in studies perhaps of colliding neutron stars, though no neutrinos were seen from the one collision that LIGO and electromagnetic detectors have seen. Neutrinos should come from the cores of supernova explosions, and our hope is that sometime in the next few decades we will see at least one such supernova explosion close enough that we see neutrinos and gravitational waves as well as electromagnetic waves. So yes, you're absolutely right. Neutrinos and cosmic ray particles also play a significant role in astronomy.
What is the origins of the latter, cosmic rays?
They're accelerated by a number of different processes in the universe. The dominant process is probably in shock waves in interstellar space. You have in a shock wave in an interstellar gas, you have two flows that are coming together, basically, or one way to say it is you have a flow that stops, that is slowed down enormously in a shock wave, supersonic on this side, subsonic on that side. And fundamental protons, say, can bounce back and forth between the two sides of the shock. And as they bounce back and forth, that is, it gets deflected back in, deflected. And because the flow on this side is moving toward the flow on that side at very, very high speed, those repetitive reflections can boost this proton up to very high speeds. They're probably also produced in supernova explosions. They're produced in quasars by magnetic effects around spinning black holes. But
this is one of the things that could fry astronauts in long-term space, right?
Well, the concern is cosmic rays from the sun. And when Elon Musk sends his
100 people to Mars.
100 people to Mars, he wants to do it at a time of very low solar activity.
Right. Sure.
Michael.
Yeah, David. Oh, yeah. And then I'll get to you. Go ahead.
What do you think the chances are the applying gravity waves by studying the changes in pulsar rates or distances to distant galaxies and so on?
So this is another technique to look for gravitational waves. I've talked previously about LIGO. LIGO looks for gravitational waves that oscillate with periods of typically 1/100th of a second, between 1/10 of a second and 1,000th of a second. LISA, the space-based analog of LIGO will look for gravitational waves with periods between a few minutes and a few hours. This other technique that you mentioned will look for gravitational waves with periods of a few years.
Wow.
And this technique, the basic idea is you have a pulsar, which is a spinning neutron star, that has a beam, a radio beam, or, well, for this purpose, radio beam that is like a searchlight that swings around. When it swings past Earth, we see a pulse of radio waves. And it's a very stable pulse. The time between pulses is very stable because a neutron star is a humongous thing with enormous inertia, and it spins very regularly. And so it's a clock. And these pulses come in very precisely timed. When a gravitational wave goes across the Earth, this is a somewhat heuristic but moderately accurate description. You can think of the waves as speeding up and slowing down all the clocks on the Earth. And so if radio astronomers are monitoring the ticking rates of pulsars, the number of pulsars at different locations on the sky, they should all slow down and speed up simultaneously, not because that's what they're doing, but because that's what our clocks are doing due to a passing gravitational wave. So this is a wonderful technique, and the sensitivities that these instruments have today are in the ballpark where they should start seeing gravitational waves sometime soon, as they continue to be improved. So I expect that that LISA will be operational, seeing gravitational waves in the early to mid 2030s. This pulsar timing technique probably by the mid 2020s and maybe sooner. LIGO is doing it now. And then there's one other technique, gravitational waves from the birth of the universe interacted, according to the theory, with the very hot gas in the universe when the universe is about 380,000 years old. When the gas was cooling down enough that the electrons were being swallowed by protons to make a neutral hydrogen. That's when the cosmic microwave radiation that the astronomers study was produced. That's when it last scattered off matter and comes to your telescopes. The gravitational waves from the birth of the universe are predicted to put a polarization pattern on these cosmic microwaves that is very characteristic. So that pattern was discovered several years ago by a team that was put together trained by Jamie Bach, and before him, Andrew Lang at Caltech. And so they announced the discovery of this pattern that could be from primordial gravitational waves a few years ago. But it turns out it was also known that that same pattern could be produced by emission from interstellar dust. They thought they had a location on the sky where they were observing where there was low enough interstellar dust that it was not mocking up a real signal. But it has turned out, when that is studied more deeply, that it could quite possibly be a false signal due to the emission from dust. And so now that community is pushing very hard, particularly Jamie Bach's group at Caltech, to understand the dust and improve these instruments and pin down this signal. I think that's likely to succeed within the next decade. So what I'm telling you is that by the mid-2030s, we should have gravitational wave observations teaching us about the universe in 4 different frequency bands, like X-ray astronomy, radio wave astronomy, optical astronomy, and gamma ray astronomy, all coming online over a period of 20 years.
Amazing.
Oh, yeah, this is coming from the Facebook chat.
Okay.
Apologies if you've already covered this. I haven't been keeping up. According to J.A. Wheeler, if 2 spinless, uncharged black holes collide and coalesce, and if they get rid of as much energy as they possibly can in the form of gravitational waves as they combine, the square of the mass of the new, heavier black hole is the sum of the squares of the combining masses. Has this been observed in the LIGO results?
Oh man, I was going to ask that.
So I think a more accurate, so this is one way of describing something due actually to Stephen Hawking rather than to Wheeler. And the more precise statement of it is Stephen Hawking's second law of black hole mechanics. And so Wheeler and perhaps his student Jacob Bekenstein, I'm not sure, had some earlier variant that was sort of along the way toward developing this, I believe. But the key powerful result is Stephen Hawking's prediction that the surface area of the final black hole has to exceed the sum of the surface areas of the initial black holes. Because the surface area goes basically as the square of the masses, we're talking about more or less the same thing. So we are very eager to test that in LIGO. And we have, in LIGO, the team has seen now 5 collisions of pairs of black holes with ultra-high confidence, and 1 with more modest confidence. But none of them are the measurements good enough to do a decent test of this prediction. And so when we announced the first discovery, I had a lot of email exchange and conversation with Stephen Hawking over this. And he was very disappointed, as was I, that the data weren't good enough to really do a test. And we still don't have a collision where it's good enough. But I'm confident that within a few years we will get collisions that are good enough. The issue is that LIGO is now shut down to beat down the noise in these second instruments. The distance that it could see when it turned on was about 3 times less than the design distance that it could see. Sensitivity was 3 times worse. So when it reaches its design sensitivity, it should be seeing a volume of the universe 3 cubed larger, 27 times larger. So instead of seeing roughly 1 black hole collision per month when the instruments are all operating together, it could be seeing a few a week or even 1 a day.
Oh, wow.
And we'll have a huge database of colliding black holes by the early 2020s. We'll have hundreds and hundreds of them. And somewhere in there we will, I'm pretty sure, have a few that are good enough that we can do a real test of this prediction.
How is Stephen doing? Is he still working actively?
So he's put most of his effort in recent years in, like I am, into science communication. I mean, I'm doing it through collaborations with filmmakers, artists, musicians. He does a lot of it through TV and film and lectures. And so he also, however, has a major research program that he's been doing with Andy Strominger at Harvard and Malcolm Perry at Cambridge, trying to understand the information loss paradox, some aspects of the information loss paradox, loss of information.
Didn't you guys have a bet about that? Was that the one?
Yeah, we had a bet about that. And on that bet, it's with John Preskill at Caltech. John is on one side, Stephen and I are on the other side. Stephen threw in the towel. Stephen had originally predicted that information would be lost back when he was visiting my research group in 1975, a long time ago. He threw in the towel and conceded that information is not lost down black holes. I've not thrown in the towel. He's a lot smarter on these issues than I am, but I think I suspect he's wrong still. But as I say, he's smarter than I am.
I mean, speaking about science icons, what do you attribute his superstardom? It's incredible.
I think you can answer that better than I can.
I don't know.
Yeah, I mean,
Yes, sir.
he really is phenomenal.
Yes.
A phenomenal scientist. He's
Yes,
really a phenomenal
yes.
scientist. But yeah.
Will gravitational astronomy shed any light on the nature of dark energy and dark matter? No pun intended.
We don't know. It could be one of the surprises. So Lisa Randall, who I think you've had here in one of these events, has suggested that there might be that there are possibly several different species of dark matter, and that some of it may be self-interacting. That would just mean it could form condensed objects, dark stars, if you wish, out of it. And this self-interacting stuff, she argues, may go into a thin disk, a much thinner disk than the thickness of our own galaxy, and may be concentrated in there. If we saw somehow gravitational wave sources that were concentrated in thin disks, that would conceivably be an indication that you're getting gravitational waves from some form of dark star or from black holes that form from collapse of dark stars. These are just wild speculations, but it's an indication it's conceivable, but we don't know enough about dark matter to know. Dark energy, the issue for understanding dark energy, a key issue is measuring the rate of expansion of the universe, going back to when the universe was a few billion years old instead of the current 13 billion years old, a very accurate measurement of the expansion of the universe, because the dark energy manifests itself by its influence on the expansion. And so astronomers are working in every way possible to measure that. We have a whole new way of making those kinds of cosmological measurements now, from a combination of LIGO and observational and electromagnetic astronomy. LIGO has seen one pair of neutron stars that spiraled together, collided, and merged. And from those observations, you determine the distance to the source, more precisely what astronomers call the luminosity distance, a particular version of the distance. Electromagnetic astronomers have a hell of a time measuring distances, but they can measure the redshift, the rate of expansion of the universe, the rate at which things are moving away from the Earth. If you can measure the distance and the redshift on a bunch of different sources, that would give you the expansion rate of the history of the expansion of the universe. The key is measuring distance and redshift. So the electromagnetic astronomers get the redshifts, we get the distances. And that's been done with one source, a pair of colliding black holes, last August 17. And it was a fantastic event where it was something like 10% or so of all of the world's astronomers were involved in observing this thing.
Wow.
LIGO discovered it. It was seen with gamma rays 1.7 seconds later. Then it was seen with light, X-rays, radio waves, infrared, ultraviolet radiation. And and all those electromagnetic measurements give you the redshift, gravitational observations give you the distance. And so this kind of thing, and that was not at good enough accuracies to teach you anything new yet, but that was the first one. And over the coming few years or decades, I expect this will be a very powerful way of mapping out the expansion rate of the universe, the combined electromagnetic and gravitational measurements, and thereby getting a handle on dark energy.
Are we going to be able to use LIGO-type experiments to measure, like, do Earth observation properties of the Earth using gravity waves?
No. The problem is that there are no strong enough sources of gravitational waves on the Earth. To get strong gravitational waves, strong enough to measure, you need to have objects that are very heavy and very compact, that have very intense internal gravitational fields. The gravitational waves, in some sense, are produced by the intense gravitational fields of these objects becoming dynamical as they go around each other or collide. We don't have anything like that on the Earth or anywhere in the solar system. So I don't see any prospect of us doing anything with any sources of gravitational waves in the solar system in this century. This is going to be all outside the solar system, I expect. Of course, I could be wrong.
Yes, sir.
Yes, you spoke earlier about events and conditions that may have come about around 380,000 years after the Big Bang. And I'm wondering how much confidence you have in the precision of a number like that, not to say 400,000. And right. If that's derived from computer simulations that you just feel very strongly about.
Pretty strong confidence. It doesn't take a computer simulation. The issue is that the photons last scattered off of hot matter when the matter was ionized, when you had a lot of free electrons floating around, and the photons scatter off the electrons. When the universe was very young, it was so hot that everything was ionized. You had a humongous number of free electrons. As the universe cooled, the electrons recombined onto the helium nuclei, onto alpha particles, at an earlier phase. And the last thing to happen to losing electrons is they're combining onto protons to form neutral hydrogen, and then they're gone and no more scattering. The theory of that recombination process is simple enough, you don't need computer simulations. And we know enough now from observationally about what the temperature was as a function of time going back, that you can pin that down quite well. That's one of the weird things. Certain things in cosmology can be pinned down really well just with some knowledge of fundamental laws of physics, some even analytic calculation without simulations, and adequate astronomical observations. And this is one of the 380,000 years. I have a lousy memory. I hope I got the 380,000.
I think that's right. Yeah.
I think I have it right.
I think that's right. Yeah, right here.
A dumb, big picture, non-math kind of question. But so, gravity slows time. Lots of mass slows time. Big Bang. Lots of mass, things small space. And we talk about 1 microsecond, 1 millisecond, 1 second, 1 year, whatever, after the Big Bang. Is that unit of time after the Big Bang measured in the location where the Big Bang was, or measured as my watch would perceive it miles away, or what does that mean?
Yeah, so
I don't even know if I'm asking the right question.
No, it's an excellent question. It's an excellent question. So physicists have developed conventions for answering things like this. When we talk about time since the Big Bang, it's the time that would be measured by clocks that move with the average motion of the matter in their vicinity. And so they're at rest with respect to all of the matter in their vicinity on average. Equal numbers of particles moving in that direction, this direction, whatever direction. And start ticking at the Big Bang and move in that manner and reach us here today. And so that's the meaning. And if you were to measure it with some clocks that moved in some other manner, you'd get a different answer. So, but this is the natural kind of clock to use. We call these the clocks of fundamental observers. We have jargon in this field. So the jargon is fundamental observers, or the observers who move with the mean motion of the matter locally. And because the universe is seen to be very homogeneous, it actually doesn't matter. We are pretty sure it doesn't make any difference whether it's a clock that began at this location and moved with the mean motion of the matter to here, or from there to here. The number is going to come out the same. But the key thing is that it's a clock of a fundamental observer who's moving in that way.
having just watched Interstellar last night, the whole key to the movie was they were going to get some information that they had to get from inside the black hole, quantum gravity. And then with that information, they were going to be able to control gravity so they can take the spaceships and all the humans to the future, then don't know how to do it.
Yes.
So what was the key that they were trying to get from, that they could only get from inside the black hole?
Read my book.
No, I like
I
that.
think you can buy it for $17.90. The word that is used, that Christopher Nolan chose to use, or the phrase he chose to use in the movie, is the quantum data. So the backstory is this: that that Professor Brand and Murph, who are the two theoretical physicists back on Earth, they have looked at all the gravitational anomalies seen on Earth and have concluded the only way they can imagine that these are produced is through some sort of influence coming from the fifth dimension, from outside our universe. And so the key to understanding then how to control gravity, how to control the anomalies, is to understand the laws of nature in the higher dimension, in the fifth dimension. And those laws of nature in the fifth dimension, the first step in that is general relativity carried into the higher dimension. So they're working with the laws of general relativity in 5 dimensions. The 3 familiar dimensions of space, time is a 4th dimension, and the 5th space dimension going out of our universe, the bulk, so-called, or the 5th dimension of the movie. And they know that inside of that these laws in the 5th dimension, the classical laws, non-quantum laws, if you understood the quantum laws, you could deduce the classical laws, and you could deduce everything. Singularities are governed by the laws of quantum gravity. And the singularity inside a black hole, they speculate that it being governed by the laws of quantum gravity, their information about how the laws of quantum gravity work in 5 dimensions will be there near the singularity. And so what they're after is the laws of quantum gravity in 5 dimensions. And so TARS, the robot who can collect information a lot faster than any human, falls in along with Cooper, collects the data about the laws of quantum gravity in 5 dimensions, and then Cooper transmits it back to his daughter. And so what they really want in the end is an effective field theory that arises from the laws of quantum gravity in 5 dimensions. And this is what I discuss in my book.
And this is a Hollywood movie seen by 100 million people. This is it. It's really stunning.
Well, you can understand why Emma did not want my book to be known before the movie came out.
That's amazing.
No, it is phenomenal that Christopher Nolan can make a movie that has where the backstory is this sophisticated. But it's real science. It's sophisticated. And where there are a large number of things that go on that are really involve very deep physics. And that can entertain 100 million people and inspire huge numbers of young people to become interested in science. I mean, it's phenomenal what he did. He has a skill as a storyteller and an ability to tell a complex story and make it moving and capture a very broad audience, despite the complexity that's underlying it, despite the fact that they go away totally puzzled about the ending of the movie.
Unless they see it 5 times. I got that snippet back in that early conversation.
7 times.
7 times, that's right. Well, I mean, it really puts the lie to the idea you have to dumb down to the general public and all that. You don't.
No, it really does. And one of the most interesting things I've done in recent years was a conversation I had over lunch for about an hour and a half with Chris and Emma about a week before the world premiere. And they spent the entire time, those 90 minutes, talking about what happens if this movie flops. Do we lose creative control of our next movie? Or can we have 2 flops before we lose creative control? But that was the central issue.
Interesting.
And they have creative control. They can do things like this because they have always made big money for the studio, for Warner Brothers.
Right.
And so the Warner Brothers executives give them pretty free rein, like they don't give to almost any other movie maker.
Right.
And Chris uses it to make a movie like this that I don't think hardly anybody else in Hollywood would be allowed to make.
Right. Well, maybe it's sending a new trend.
Yeah.
Yeah. Well, thank you for doing that. Okay. Well, we've been going almost 2 hours. Thank you, Kip, for coming out. Thank you so much. Thank you for watching. Check us out at skeptic.com and support our mission to promote science and critical thinking at Patreon.